Now let's say that you want to make a simulation or a model. There's various routes or roads that you can take. On one hand, you can take the hard road and you could start completely from scratch and try to solve everything. On the other hand, you can tackle a very specific problem that isn't solved. This is easier, but it will of course have restricted validity. You could, for example, just focus on how a specific kind of planet forms, specific kind of star forms, or a specific kind of galaxy forms and evolves. Regardless of what you're doing and how you're doing it, typically you want to then take some observables and try to match them with some free parameters, essentially to try to constrain your model and test how good it may be and also how useful it might be to learn real things about the universe. And perhaps you're really keen in terms of using the full physics, which will be very, very time consuming. Specifically for cosmological simulations, then almost all simulations rely on this backbone of dark matter that you can see here. These simulations that only contain dark matter are typically referred to as n-body. You can do n-body simulations that are not just of dark matter, of course, but some of the largest n-body simulations are of dark matter only, where you're just following gravity and what it's doing. You can very easily understand why you'd want to do this. This is because dark matter will dominate the matter component. So to first order, this is the most important ingredient. However, as we've seen before, galaxies and other structures don't just follow dark matter, because baryons, especially at small scales, will have very important effects because they will be able to cool down the gas to form things like stars, and stars can go supernova, and you can also form supermassive black holes that will have a huge effect. But one important thing to address is that typically when you heard about dark matter, perhaps you also heard about the term cold dark matter. But why should dark matter be cold, and what does that even mean? I mean, if dark matter doesn't radiate, why do we call it cold? Turns out that dark matter, in principle or in a theoretical sense, can actually have different temperatures. These temperatures are not the same as for baryons, but rather they have to do with the typical velocities, which also have to do with the typical mass of individual dark matter particles. For cold dark matter, it means particles, individual ones, are quite massive, and therefore they're moving slowly, so you can associate the temperature with it and it being cold. And if you're looking at warm or hot dark matter, it means the individual particles will be even smaller, and therefore the typical velocities will be higher. These will have enormous consequences in terms of how the structure of the universe from a dark matter perspective grows. For example, if the universe has hot dark matter, then the structure will be suppressed and essentially have way less very massive clusters and many more substructure that does not get as dense. While if you're looking at a universe dominated by cold dark matter, then you expect to get big clumps that become very dense. That's just because dark matter particles will be able to move slower, and therefore they can very easily form more dense structures, and away from them you'll get some very large voids. And it turns out that by comparing the real universe with different n-body simulations, cold dark matter particles seem to be the ones that explain our universe the best, at least currently. Once you establish that dark matter should be cold, you can then run your n-body simulations, and you can actually establish how structure grows with time, and also to find different scales of structure. And using this, you can then use different approaches to see how you populate these dark matter webs and the nodes with baryons, and then follow all the physics. In sections 13 and 14, we've seen how if you just use dark matter and you associate every node with a galaxy, then you actually overpredict the number of faint galaxies and the number of high luminosity galaxies. And given the physics of dark matter and baryons, we do expect them to behave very differently. For example, baryonic gas will be able to collapse much further because it radiates, and we will reach much higher densities. And while baryons follow dark matter, they will very quickly create smaller scale substructures, and they will start forming stars, while dark matter, even though it is cold dark matter, it is not cold enough to ever form stars made of dark matter. On one hand, we can determine the cold dark matter halo mass function very well from cosmological simulations and body simulations, but this is, as we've seen, much steeper than the real galaxy luminosity function, and it's much shallower at the bright end. And as we've seen, we can actually reconcile the predictions with observations by invoking processes that involve the release of a lot of energy from baryons that we called feedback, stellar feedback and AGN feedback. The main idea behind feedback that we covered already in section 14 is that there will be energy released, and for supernova feedback, this release will be coming from evolving stars, but also from AGN feedback, this energy release will come from massive, supermassive black holes. If you do the calculations, you know that such effect is actually energetically possible. There is enough energy to actually affect the galaxy-wide, either from supernova and from supermassive black holes. And this is because the energy released is in many cases comparable to the binding energy. It means you can actually throw away the gas that never comes back. However, this is also challenging, and it's challenging to understand because much of this energy can actually be radiated away without actually affecting, for example, the gas. Even though there's a lot of questions about how these work in practice, the two main forms of feedback that we already covered in section 14 and that are now crucial to simulations are supernova-driven winds and also AGN-driven feedback. But there are other kinds of feedback, for example, reionization, that we are not covering in Physics 263.